Thanks a lot, John, for the introduction. Good morning, everyone. What I like to do today is to talk about a couple of lessons we learned in building Spark streaming application at Microsoft BingScale. So the application is developed in Mobius. Well, it doesn't move. Anyway, we have a Mobius talk tomorrow afternoon. If you guys are interested, please join us. And okay. 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 Got it. Thank you. So back to the slide. The application itself is part of a bigger Lambda architecture, where the same set of C# libraries are shared from an existing batch processing pipeline. So as you can see, we have 3 topics of raw logs. First one is H, which is the query event, and the UI layout of the query, and the click, the related clicks for the query. So they are coming from a couple of Kafka clusters worldwide. So we want to join the 3 topics on a common global unique ID within a predefined time window. So by the predefined time window, we mean the query event will, once it comes, it will wait for a predefined time of, for example, 10 minutes for its related clicks to come. When the query event running out of 10 minutes time window, it will run through a merge pipeline, apply further business logic, and eventually output a destination Kafka queue for downstream consuming. Please note the 10-minute window there is actually based on application time or event time, meaning the time when the event actually happened instead of system time. So the first problem we are facing is we found that application time is not actually naturally supported in Spark 1.6. So all Spark APIs are actually system time based. So meaning that we cannot simply use the native join API for our application time based operation. So we decided to use the update state by key API instead. So although it's also system time based, it actually allows us to plug in a user defined join function. So in which we can enforce the time window based on application time. So here's the graph, the brief look how it works. So basically the update state by key maintains a partially joined events as the state. So the state keeps joining with the new coming events until the query event itself is running out of the 10-minute time window. So once it's out of the 10-minute time window, it will output to the destination Kafka queue. So looking at the procedural code, it actually shows how that application time is enforced here. So for the application time itself is extracted from the timestamp field of query event. And first, among all the new events, so we get the max event time of all the incoming events as the current time. So then we use the current time to determine whether a particular state is out of many time window or not. So that's how it works. To enforce application time in this join function. So to summarize, update by key API is actually the right application and the right option for application time-based join operation. And it actually works just fine as expected for us. So let's move to the next slide. So that's lesson 1. Let's move to lesson 2. So the problem with the first actually performance issue we are facing is that unbalanced Kafka partition causing delay in the pipeline. So we'll use a direct Kafka approach to fetch data from Kafka queue. So as you guys know, in Spark streaming, Kafka RDD generates only one RDD partition for one Kafka partition. And it will actually wait until the last RDD partition to complete its task before it can move on to the next stage. So this can cause overall delay in streaming jobs if Kafka partitions are unbalanced or under-distributed. To make it worse, the delay actually accumulates from batch to batch, and the application eventually went into unstable state. So by unbalanced partition, we mean one or more Kafka partition actually has n times more data than average, so which can cause unnecessary delay in the streaming job. So please note, while waiting for the biggest RDD partition to complete this job, most other tasks are actually done. So leaving that Spark cluster utilization is very low. So next, by under-distributed Kafka partition, we mean that the data size is too big per partition, so causing the streaming job not able to keep up with the incoming data. So we tried that native repartition API to try to solve the problem. It helps a little bit. So we use the API to actually redistribute the data evenly across a good number of RDD partitions, hopefully to solve the problem, unbalanced problem. It helps a little bit, but very limited because of the extra, shuffling cost it introduces. And it doesn't actually solve the unbalanced partition root cause. So as a result, in the graph, it still could not finish the job in the batch interval time. So we realized that a better approach should be actually repartitioning the data in the first place without any extra shuffling cost, and then remove the unbalanced partition root cause completely. So that means we need to actually step into the code, the platform code, to override RDD's well-known get partitions method to apply a custom partitioning algorithm with a predefined threshold. So meaning if a Kafka partition has more messages than the threshold, it will be split evenly into multiple offset ranges. So in other words, there can be multiple RDD partitions will each read one of the offset ranges of the same Kafka partition. So this actually achieves the same result as the native repartition API, but without extra shuffling cost. So after we apply this approach, so that average processing time drops within the batch interval time. So the application back into stable state again. One thing to note about here is that the repartition, including the native repartition API, no longer guarantee the global ordering of the Kafka data. So if your application requires global ordering guarantee, you probably need to fix the Kafka partitioning in the first place, and to have a better distribution in the first place, Okay, let's move to next. So on time, Kafka Fetch job submission. The problem is overall job delay accumulates due to transient, slow, hot Kafka broker issues. So as we enable the full scale of input data, we observe that there were almost always, a few random slow or hot Kafka brokers. Very slow, much slower than all the other ones, due to some unknown reason, regardless of the partition size. So this is a different issue than the previous one, but has the same negative impacts on the application's stability. So we tried that the well-known speculative task, but it didn't completely solve the problem. Why? But it's a little bit complicated. If you guys are interested, we can discuss offline why this doesn't solve the problem completely. So, it's okay to have a job, for the job to actually have some delay, but we don't want the delay to accumulate. That will cause unstable application. So then we tried enabling the undocumented concurrent jobs to try to stop the delay from accumulating. So believe it or not, it worked, for us, as expected. But there is a little problem. The concurrent job doesn't guarantee the batch ordering required by our update state by key based application. So basically, the application has two stages. One is the Kafka fetch, to fetch the data ingress, plus update by key stage. So out of the two stages, update state by key can actually start. It has to wait for the last batch to complete before it can start. Otherwise, the checkpointed based state can be messed up. Again, this one it's a little bit complicated. We can discuss later offline why it happens. So, but the first stage, a Kafka fetch stage, doesn't have the ordering requirement. It should always start on time at the batch interval. So we decided to leverage the underlying Spark parallel job feature directly to achieve the purpose. So that means we need to actually step into the platform code again to override one of the well-known method of the D stream to actually try to submit the job to submit the job in a separate thread. So in order for that Kafka fetch job to actually start running instead of waiting in job queue. So this approach actually stops the delay from accumulating as well, just like the concurrent jobs does, but still guarantees the batch ordering. So if you look at the graph, the batch B, so it's Kafka fetch job start on time, even if batch A not completed yet. That means what? That means actually, although the job can be delayed like batch A, but the delay doesn't accumulate anymore because the batch always starts on time. Batch C as well actually starts Kafka fetch job on time, but after it completes its update state by key stage, doesn't start. Actually, it won't start until the previous batch B completes its work. That means the batch ordering guarantee still observed here. So that's exactly what we want. So it's great. The approach successfully stops the job delay to accumulate, but while still observes the batch ordering requirement. Okay, let's move on to the next one. So fetching Kafka metadata from multiple data center often takes more time than expected. So this is again, and probably triggered by the full-scale input data. So in our application, the input stream is actually a union of a couple of Kafka streams created on a per topic, per Kafka cluster basis. So it turns out that Kafka metadata of all topics from all clusters is fetched sequentially, one stream after another. So this can take minutes to complete. So actually this impacts the overall performance significantly, and also causes, the streaming UI tab not responsive. So we realized that a much more efficient approach would be to let each Kafka stream fetch its metadata in its own separate thread. So it's no longer blocking the batch. It actually can run in parallel with the batch instead of blocking the batch. So the solution is actually customize or subclass the Kafka direct input dstream platform code and move metadata refresh to a separate thread, like the procedural code shows. It actually refresh metadata and in a separate thread, and put the results, the offset ranges of a Kafka topic into a queue, and for the dstream to pick up. So the rest of the dstream works exactly the same as before, except that it picks up that offset range from the queue, and they continue to generate the RDD as usual. So to summarize a little bit, so this approach successfully stops a metadata fetch from blocking the streaming batch job. So next one is actually very close related to the previous lesson. So the problem is the Kafka fetch, data fetch, and the data processing not in parallel. So today, under direct Kafka approach, so Kafka data fetch and data processing are running sequentially, one after another, while they should be fully in parallel, because one is the I/O and intensive job, the other one is a CPU intensive job. For the Kafka fetch, there's no reason for it to wait for the data processing to for the next Kafka fetch job doesn't have to wait for the previous data processing job to complete. So they should running in parallel. So this one, we actually took lesson 4 a step further, because in lesson 4, we already refresh the metadata in parallel, in a separate thread. So if the thinking is, if after fetching the metadata, we further generate and materialize the RDD, we can also parallelize Kafka data fetch as well. So looking at the code, within that separate thread, actually, after refresh the metadata, we actually materialize by running the job and cache it for this stream to pick up. So when this stream create the job, so that the fetch data is already there in the cluster. So it doesn't have to wait for the data to come. So what does this mean? This means that we can parallelize data fetch and data processing efficiently and with limited code change. As you can see, the code change is very limited, but without cost like write high log. the native Kafka receiver, does. So we actually take advantage of both direct approach and receiver approach, but without the disadvantages of both approach. Okay, that's all I have today. So running a little bit earlier. So if you guys have any questions, please feel free to ask.
And I'll bring around the mic for people with questions.
Do you have plans to contribute the changes back?
Yeah, we do. Yes, we do. But some of them are still in very early stage. We're still, testing, experimenting.
What you said make a lot of sense to me. All the tips. Thank you very much. First, I do have a few questions. The first question, I think, regarding number 2 in your slides. I just want to confirm that when you say you do dynamic repartition, is that per iteration, right? Like per fetch, you can, based on the threshold, you can dynamically to decide whether how many partition you split into, right?
Right.
Oh, okay, cool. All right, so then I think go to the first slide, the map, the update key with state. Have you? I wondering. Have you tried the latest map with state? The function, I think, is a replacement of this update state by key. It's doing the similar thing to update, maintain the state information.
Yeah, that's a good question because they're basically doing the same thing, except that the map with state, they actually embedded the logic on platform side. So here we actually do that on application side. So it doesn't really make any much difference for our case.
Okay. Yeah. One of the problem even was, I read the paper. They say the map state was key, whatever, has better performance. But even with that, we experience. I think a lot of time the memory doesn't get released in time, so it's like even the actual memory we need to store the data, the stateful data, maybe is like say 1 gig, but because a lot of transit RDD still hang around, we have to use much more spaces.
Okay.
So do you have any problem with your implementation and how do you, like, for example, the frequency of controlling the checkpoints? You want to share some experience with that?
Actually, it's not fully applicable to our application because we are developing in Mobius. So the optimization you're talking about is actually the Scala native implementation. Okay. So that's not actually applicable to us because we're actually running that logic on C# side. Okay. So for the checkpointing, yeah, so we can, checkpointing is a little bit complicated. We can discuss more, that one. We do have issues regarding the checkpointing.
All right. So let me ask one more question. Excuse me. So at the end, the 4 and 5, you say you try to enable the parallel of fetching data and the processing. I think that's good in certain case, but I think there's one way to not doing that is sometimes, let's say you do require a lot of computation time, you don't have enough CPU power to do it. If you have a lot of parallel jobs, fetching the data, but without the ability to process them in time, you end up, power up your memory. And bigger way running Java, I think that everyone know that Java has a bad garbage collection process. So sometimes you want to avoid that. You want to only fetch the data when you have the time to process them.
Yeah, that's a good question. Because, the back pressure, right? So, that's a bigger problem for the native receiver mode, where it's just, regardless of the processing, just keep receiving data. But in this case, we call it a direct receiver. We do have a simple, back pressure. Back pressure is simpler to handle here. So there's some synchronization between the receiver and that RDD of the D stream, job generation in the actual implementation. So that back pressure is not quite applicable here in our case.
Was there one question over here? Oh, yes, your question. Okay.
Yeah, just wondering, is a Kafka, to use Kafka is a must, or can you avoid Kafka because Spark you have dstream and dataset and all this stuff? So just curious to know. Or there is any alternative than Kafka as well? Thank you.
I don't have, but I think right now, there's other things I'm not very familiar, like Flume something I've heard, but Kafka is our major, input. It's not actually within our control. We just have that input signal from Kafka.
Other questions?
Hi. I was wondering if your streaming application requires you to skip certain input. For instance, if your job gets delayed due to some reasons, and there is a need to not process something. Like many times, streaming application, we want data to be there, results to be there, but not necessarily consistent. But since we are ingesting live data all the time, like real time, if it's a real time application, then
Yeah. Yeah, that's a good question too. We do have, some policy. For example, dropping policy. So we just, keep running. Get data, set a threshold there. If we're running out of the threshold, we just, ignore it. And then we also have something you can pick the bug. You can actually write some let's say rolling task, to rolling to the next batch.
We have time for another question. Anyone else? In the back.
Didn't fully understand on step 4, your lesson 4, where you're saying you're going to parallelize the next stage before you're going to launch the next batch. Is that correct? You're parallelizing. You're launching the subsequent batch before the first batch. You're going to launch batch 2 before batch 1 finishes.
Yeah.
So what if batch 1 fails? Then how do you know that you have to go back? It seems like you're kind of just keep moving forward without regard to see if a batch fails, and then you're going to have to re-pull those same events off of Kafka. Batch failure is something we deal with a whole lot, that we have to make sure we process everything at least once. If batch 1 were to fail, it seems like batch 2 has already gone ahead and start doing his thing at the next offset. So batch 1 gets events 1 through 1,000, and batch 2 is pulling events from 2,000 to 3,000 without caring if batch 1's going to succeed or not.
So you're talking about this guy?
Yeah, that it seems you're launching batch 2 before batch 1 completes. That's how you're getting some extra gains by parallelizing. You're starting to fetch while batch 1 is still processing. Did I understand that correctly?
I think that's this guy.
Yes. Okay. Perhaps
this one,
lesson
right?
3. Right.
Let me overall job. Yeah. So actually not. It's the batch ordering logic is not being touched. So most effectively, if you look at do I have a procedural code here? That batch you started on the Kafka data fetch job, right? It started on time. It's actually, that part is not the batch yet. So we actually fetch the data during the job generation time, not runtime. So it's not actually part of the batch yet. So we explicitly call the run job API to actually materialize the RDD beforehand and cache it. And then the actually job generation is still part of the graph. So it's outside of the batch. It doesn't affect, the batch ordering logic. The only difference is before we generate the job, we actually materialize the RDD. After the RDD generated, we materialize it. That's the only difference.
So as soon as batch A finishes is when you kick off batch B fetch?
That one batch is not actually kicked off. We just run a separate job separately. If that particular batch failed, the result is just gone. We don't use it.
Awesome. Let's give him a big hand.